It's the cool thing to do. And I never figured out what it is. What is modular? And so I was trying to figure out what is so wonderful about modular representation theory. And this is somehow my solution to the question is, well, I cannot think in terms of modular representation theory, but I like to do computations. I look at Mark Shimazona. We grew up with Adriano Garcia, and we just do computations. And when I do computations, there are things, for me, if I see this, I just have to write x is square root 3. I don't worry about whether square root 3 doesn't exist. Or the same, if you see something like this, you just write automatically. You just write this thing. It doesn't matter. You have to write. So this is what universal Verma modules are for. I want to do some computations, and I just find a place to do them. So I will start with U will be UQGLN for most of the talk. So U is made of 3 parts: U less than 0, U greater than 0, and U0. So U less than 0 is generated by the f's, f1 up to fn minus 1. U greater than 0 is generated by the e's, e1 up to en minus 1. And u0 is generated by, well, u0 is some field adjoined some variables L1 up to Ln plus minus 1. And there are relations. So with relations, which tell me how to move all the f's to the left and all the e's to the right. So for example, EIFJ minus FJEI is delta ij times Li plus 1 inverse minus Li inverse Li plus 1 on Q minus Q inverse, etc. So there are more relations. So that's the quantum group GLN. Now, you see what the problem is here is I don't like to work in this place. So I just want to change it, and let's add the denominators. We allow ourselves to work in a slightly larger. Of course, when we do that, when we allow denominators, then this quantum group just becomes this object, right? Where you can write denominators in the L's. So then the universal Verma module, M, it looks to me like the negative part of the quantum group times a highest weight vector. So so this is the U module generated by some vector m plus with EI m plus equal to 0. Okay, so that's the universal Verma module. Now, I can view this as a vector space over K, in which it looks just like the negative half of the quantum group, or I can view it as some, whatever I need to do with K. So let's just make a remark here that if you have a sequence of numbers, then you get two kinds of things. You have sigma mu is a map from K to K, which takes Li to Q to the mu I Li. And evaluation sub mu is the map from K to this your base field, which evaluates at Q to the mu I. So I think of so these are our automorphisms, and characters or evaluation characters. And of course, when I think that way, then the Verma module is just the evaluation of this module M. So this is, okay, so this is the Verma of highest weight module. Of highest weight. So that's why I call it universal Verma module, because if I evaluate at mu, then it's my Verma module of highest weight mu. But I can just do computations here. Now, of course, you should probably complain that sometimes when I evaluate, I might get 0, so just avoid those places. See, I don't worry about that. Just so you can localize at some place away from this bad points. And okay, so that's the universal Verma module. Now, what I really want to study is translation. So translation by V. So let V be the U module. So this is a GLN. So U is UQ GLN module with basis. So the basis is B1 up to Bn, and the action is the ordinary action on the fundamental representation. So Q to the delta ij, bj. So they are weight vectors, and EI, bj is delta j I plus 1 bi, and Fi, bj is delta ji bi plus 1. So it's the usual n-dimensional representation.
Sorry, did you say this evaluation, this is a map from K mu to QQ. So what does it mean to apply it to M?
So all the stuff in K
Apply it to this K.
becomes, if you like, QQ. But if I'm viewing that as a vector space over QQ, then I just don't write that because they commute with everything. I have to be a little bit careful with the K's because they don't commute with everything. But okay. So now I can translate by this module. So the game is find highest weight vectors. Highest weight vectors in this case are invariants for the positive part in M tensor V. And we do this really, let's try to do it explicitly. Let's just compute. So we want vector n1 is M plus tensor B1. Certainly that's, if you act by the e's on this, then it will die, because M plus is highest weight, or M plus is a U greater than 0 invariant, and B1 is a U greater than 0 invariant, the tensor product will be. And then you find the next one. Well, you would like it to be this, but it's not quite, so you have to correct. So there's some U2, 1, and 1. And then you find the next one, which is M plus tensor B3. But then there's, oh, I forgot to say, this is all joint work with Peter Tingley. So if there's any confusion in the formula, ask him. N2 plus U3, 1, and 1, and so on. So we just look for these vectors, and the condition I want on the vectors is that they are with E, I, N, K equal to 0. So this is for all I up to N, and N minus 1, and K. So it's, I mean, it's not too difficult to argue that you will get exactly capital N of them. There will be one such highest weight vector for each basis element of V. And its top term will be this. We'll normalize it to be that. So these U's will be inside inside this space, U less than 0K. Okay, so what are they? So let me see if I can tell you the answer. So this is the theorem. So I need some notation first, of course. So this Q analog of X is X minus X inverse over Q minus Q inverse. And Lij, I will let that be Li Lj inverse. And I will need epsilon I will be the vector which has a 1 in the ith place and zeros everywhere else. And rho will be n minus 1, n minus 2, 2, 1, 0. And I need the PBW basis, so Fi, I plus 1 is Fi, and Fij is Q Fi plus 1 J Fi minus Fi I plus 1 Fi plus 1 J. And I remember that sigma mu means the automorphism which takes Li to Q to the mu I Li. Okay, with this notation, let me tell you the answer to the U's. So the U's are, I will need a the sum over subsets of j plus 1 up to k minus 1. I'll take Fia1 up to Fia1, Fa1, A2 up to J, sorry. So you should think of the subset is A1 up to AL. So I just take this subset and I take the product of the elements JA1, A1, A2, A2, A3 up to ALK in the PBW basis. And then I'm going to put some stuff here which is in K. So this will be sigma of rho of L, Q analog of L JA1 complement up to LJAM complement divided by LJA1 up to LJAL times LJ plus 1 up to LK divided by sigma epsilon j plus 1 of LJ plus 1 up to sigma epsilon k LJK times Q to the minus 2L minus M minus 1. I think that's right. So and A complement. So A complement is the complement of the subset inside J plus 1 up to K minus 1, and I label that as A1 up to AM complement. Okay. So the point, it doesn't really matter what it is. The point is you can just compute these vectors. And when you do the computation, you need some numerators and some denominators. If you want vectors that satisfy that condition, this is what will come out. And I don't guarantee the formula because Peter has not properly checked it, and I tried to I tried to massage it in some way that he's not familiar with yet. So ask us tomorrow. We'll check. So A is the subset that I chose, and A complement is the complement of the subset that I chose. And I label the elements of A complement as A1 up to AM with C's on them. So I'm not sure if it's the best notation. I'm still fighting with the notation.
And then in the brackets, L sub j.
So that means this. So Lij bracket is Li Lj inverse minus Lj Li inverse over Q minus Q. Yeah. So it's it doesn't. But you can just compute it. And it's some mess. Okay. All right. So I want to make a little remark about the proof of this. So you use these relations to.
There's no denominator?
There. Oh. Yes, there are certainly denominators. So, sorry, but there are brackets. I forgot the brackets. There are brackets missing there. Yeah. No, there have to be denominators because. Yes. So you use these to put conditions, to write conditions. On the UKJ. And then you look at in Brundon's thesis and then steal the formula from Brundon's thesis. So the paper is called Modular Branching Rules and the Molyneux map. And if I understand right, Sasha, this is the Q analog of your thesis, or certainly your Krella papers. So this is the Q analog of Sasha's work on modular branching. So the point is that I don't know any modular representation theory, but somehow I'm doing it because they say that I am, right? All I did is I computed something. Okay, so you steal this, and that's the formula. The only reason I'm having problems with the formula is because I've changed the notation from Brundon so much that I've gotten lost. Okay, so that's the game. And now the next part of so now we are entering part 2 of the talk, and part 2 says that we are going to make a connection to Fock space. But there's already, if you know the game, already in these modular branching rules, that should not be a surprise. There should be a connection to Fock space here. So let me make the connection the way I want to say it. So contravariant forms. So a symmetric bilinear form on a U module, let's call the U module P, and let's call the form bracket, is contravariant if it satisfies that the U's can move from the left to the right, but when they do that, when they move, they're acted by this involution. So where tau is the automorphism, so I want to take it to be an algebra anti-automorphism, and I want to take it to be a co-algebra automorphism. And it's essentially the Cartan involution normalized so that these things are true. So it's tau of EI is minus Fi Li plus 1 inverse, and tau of Fi is minus Li inverse Li plus 1 EI, and tau of Li is Li. I think those are right. Okay, so then let's let bracket M be a form on the universal Verma module, and bracket V be a form on V. And so be contravariant, and with we'll normalize it so that the highest weight vector has inner product 1. Okay, so then I can define a form on the translated module. All right. And this will have values in K. It will be K bilinear by just taking the tensor product of the two forms. So this is M1, M2 under the M inner product, and V1, V2 under the V inner product. And that defines a form on M tensor V. And this choice was made so that the tensor product form will be contravariant. See, this is a philosophy that I remember the first time that I met Zorgel. I said, if we want to prove Kazan-Lucid conjecture, I don't understand what's so hard. You have to, you're trying to measure depth in the Janssen filtration, so you're trying to measure zeros of such a contravariant form, and you want to figure it out. Well, let's just translate and compare the Janssen filtration before and afterwards. And if I get some control there, then I can have a hope of understanding how does Janssen filtration act. So these are the contravariant forms of which I'm going to study what the filtration with respect to that form. So let's say a little more. So in this language, my ends have disappeared. But you remember that my ends. Okay, so I've taken my ends. And what I'm going to do now is I'm going to look at the shadow of these ends under the form. So these are shadows of the highest weight vectors. So what I mean by the shadow is I'm going to just take the inner product of nk with itself. So these are some very specific vectors. I gave you a formula for them. Take the inner product of these vectors with themselves under this form. And so this is the formula. L1k, L2k, up to Lk minus 1k, divided by sigma epsilon 1 of L1k, sigma epsilon k of Lk minus 1k. And I need to take the row shift of all of that. Okay, do you remember what the sigmas are? So sigma is this automorphism that shifts Li to q to the mu I. Okay, so here's a number, or here's an element of k. But this element of k has some information about those highest weight vectors. I don't need to remember the whole messy formula for the highest weight vector. It has some information. All right, so the second part is, so let's evaluate that. So remember now, Well, let me let mu be a partition. And I'm going to, so I'm thinking of, here's my mu. And I have these evaluation maps. So mu I is the number of boxes in row I. And remember, evaluation mu will send me to ordinary fractions. And what we can do is we'll take the evaluation now, so this is even more of a shadow of that vector. And this is the product over j less than k of mu k minus k minus mu j minus j minus 1, q analog. Oh, this q analog is slightly different. Sorry about that. Q analog of n is q to the n minus q to the minus n on q minus q inverse, divided by mu k minus mu j minus j. Okay, so yeah.
Is that the same formula you see with spec modules?
Yes. Yeah, hopefully I'm going to remark that. I haven't, yes, this is a Hooke formula which appears in spec module theory, yes. Okay, so, so here I just took the universal Verma module, I computed these fake highest weight vectors, or real highest weight vectors, whatever you want to call them, and now I'm looking at the shadows under evaluation at mu. Now, let's do a little more, so let's let phi L be the Lth cyclotonic polynomial. And let's take the corresponding valuation. So this takes me now from the fractions to the integers, the corresponding valuation. And that, of course, is defined by, so the definition of this valuation is that you just take the number of factors of phi L in the numerator minus the number of factors of phi L in the denominator. That's the definition of the valuation at phi L. So phi L is a prime in this in the ring of integers of this fraction field. Okay, so let's take this expression and we just compute. We just look at it and count the number of phi L's in the numerator minus the number of phi L's in the denominator. And what do you get? So then the so this is an integer which is the shadow of my highest weight vector. This is the number of removable boxes of content C. Oh, I forgot to say what is C. Above the kth row. I will tell you in a moment. Above the kth row. Minus the number of addable boxes of content C above the kth row. Okay, so here where C is mu k minus k plus 1 is the content of the addable box in row L, in row K, and all the contents you need to take them mod L in this to measure this valuation. And the contents our taken model. So let's, and I should, so addable boxes are the boxes that you can add to get a partition, and removable boxes are the boxes that you can remove to get a partition. Okay, so there we are. From the point of view of this talk here, all I did is started with M, tensor with V, look at some highest weight vectors, write them down, write down their inner products, and then take these successive shadows. And what comes out is this funny, this combinatorial statistic, which of course now is a very famous statistic. So let's write the remark. So we can, those numbers appear in the Misramiwa description of Fock space. And we can write in this notation what is the Fock space. So this is the span, and I'm going to use a new variable v of some symbols indexed by partitions with some operators, on this vector space. And these operators, you act on, let's say we act on mu by the operator fc. So fc, if you write given by. And what we do is we'll take the sum over all partitions which are gotten by adding a box, a partition, and so lambda slash mu is a box of content C. And then we'll take V to this number. So this is the inner product of nk with itself, the evaluation of it, and then the valuation at the Lth cyclotomic polynomial. And that's a generating function now for these numbers. So we just put together this little information in a generating function. And this combinatorial formula matches with Misramiwa, and so there we go. Here's a way to get these operators without knowing anything about affine Lie algebras or anything. You just compute some vectors. So so the second remark is the one which Monica said. So in particular, one reference is this paper of Arun Ram. So this is, I don't know, computes inner products on specs modules, and gets this hook formula. I don't know that probably if there are other people who have also done this, but that's one reference, and gets the hook formula. In this theorem in part B, and Ram Hansen also says that these are the numbers which appear in Fock space. So he all of this connection is there and connects to Fock space. Now our picture that so that's on Spex modules. Those are modules for the symmetric group or for the Hecke algebra. So the connection is that by Schur-Weil duality, which in this case is maybe Arakawa-Suzuki, Suzuki, and I wrote a paper with Rosa Orellana, and so the point of this is that if you take this M, well, let's take a real Verma module, so evaluate M, and then you tensor by V so you do several translations, not just one translation, but do several translations, and then you look at the highest weight vectors. So this is highest weight vectors of weight lambda in this tensor product. Then this is a Hecke algebra module. So this is by Schur-Weyl duality. So is a HK tilde, so that's affine Hecke algebra module. And the form, so you get a form, as we did over there, we get a form on this, a contravariant form, and that transfers. So the form the form when you view it as a U module transfers to a form viewed as a Hecke algebra module, and that's the spect form transfers. So the different parts of my life are starting to come together. So the Schur-Weyl duality, the Fock space, the translation, the story, and then this story of computing inner products. Okay, so part A of the theorem is now erased. So let me remind you what part A of the theorem was. So this is remark 3 now. So the part A said that the inner product of nk with nk is L1k bracket up to Lk minus 1 k bracket divided by sigma epsilon 1 of bracket L1k up to sigma epsilon k minus 1 of bracket Lk minus 1. All right, so now this is a special case. This is a special case, well, special case of a generalization. So Janssen was, of course, not working in the quantum case, but he was working in the classical case of a formula in Janssen's thesis. So let me tell you the formula in Janssen's thesis, because this is, I really like this connection back to the beginnings of the translation functor. So let's let V, so now let's think of V as the highest weight module, the finite dimensional U module of irreducible of highest weight mu, of highest weight nu. All right? So instead of translating by the n-dimensional module, translate by some other module. Okay, so let's let B1 up to BD be a basis of L nu. And I'm going to order it so that the higher weights come first. So I is less than j if the weight of bi is greater than the weight of bj. So the first vector is the highest weight vector, and then I move down in the module, creating that. All right. So then, of course, I can play the translation game. And this is exactly what Janssen says to do. So find, he didn't use the same language, but it's the same construction. So find u greater than 0 invariance in M tensor V. So M is still the universal Verma module. So that we just write them down. We just compute. N is, the first one is easy. And the second one, you have to take M tensor V2, and then you have to add some garbage. And then the next one, you take M tensor B3, and then you have to add some garbage from higher up. And you compute. So this is with EI and K equals 0. So now let's take the lambda weight space of this finite dimensional module, and let's pick out the basis elements which span the lambda weight space. So I'm just going to call them BL up to BM. So somewhere in these basis elements is the lambda weight space, and let's go find those basis elements which contribute to the lambda weight space. Okay, so then this is the statement of Janssen. It says, if you take the determinant of the matrix Ni, Nj, so this gram matrix, where now this I and j run over the lambda weight space, divided by the determinant of the original before you translate by m, then this is the product over weights. So between nu and, so nu is the highest weight, and I'm looking at the lambda weight space. So I take these, and I take so there will be a row shift, and then I take k of nu minus tau, and I take sigma tau of k of tau minus lambda, and I take that to the dimension of the tau weight space. So the k's, does it make sense what the k's are? So ki is k alpha I, and in general k mu or k gamma is k1 to the gamma 1, etc. k n to the gamma n if gamma is gamma 1 alpha 1 up to gamma n alpha n. And EI Fj minus Fj EI is delta Ij Ki minus Ki inverse on Q minus Q inverse. All right, so this is Janssen's formula. And that formula that we wrote there, oh, there was a row shift. Sorry, I copied it wrong. Is just a special case. It's so, yeah, question.
I have a question, which it might be something you're going to later, but so on like the spec module side, to get this basis of diagonalizes the gram matrix, you can get there by intertwining. You take one and hit it with intertwiner. So do you have that for your ends? Is there like an intertwiner?
No, so I'm not really choosing one that diagonalizes the gram matrix. It's just upper triangular. I'm just doing it in such a way that I can keep track of what the diagonal entries are. Now we could try to find some sort of Gelfand-Zetlin basis or something which would actually be diagonal, but that's more work. I don't want to do that right now. Yeah. Mm-hmm. Okay, so.
But you need to make a special choice of the L nu, so that the basis vectors must satisfy the kind of linear ordering of the weights.
Yeah, to do the triangularity. That's right. That's right. But that's very natural because just because of the way the filtration in M tensor V is, it's the only way to. It's the only natural way to filter M tensor V as as highest weight modules to give it a highest weight module filtration, a delta filtration or whatever you want to call it. Okay, so of course now we have gone backwards. I keep going backwards in time, right? So now we're back to about 1974 or something, right? And of course, I just will finish with, in fact, the motivation for me, well, this is remark 4, I guess, was that I was trying to understand this Gabor-Joseph story, which, so this is towards the Kazan-Lustig conjecture. Which for me was a very nice paper, because when I thought of, fortunately I was born after all the Kazan-Lustig stuff came out, but I was trying to understand, how could this Kazan-Lustig conjecture be true? How is it that decomposition numbers of Verma modules are related to the Hecke algebra? If that's true, then I must be able to see the Hecke algebra somewhere in the Verma modules. And that's what Gabor-Joseph did for me, is they said, well, if you define some operators, and I'm not going to, because I haven't introduced the notation, but let's define some operators which look like v to the valuation of nw, maybe I should put it, I don't know, of nw at the appropriate prime here, times w circ lambda plus v to the valuation of nwsi at the appropriate prime, I don't know, of wsi circ lambda, where I've chosen, where you choose v to be just the right highest weight module, which is something like this, and beta is r beta is the appropriate thing. So I won't write off. So they did exactly the same construction that I just did for Fock space, and they said this gives you an action of the Hecke algebra. So give an action of the Hecke algebra. In fact, the usual action of the Hecke algebra. On the category O, on the Grothendieck group. Group of the category O. So in that sense, this Fock space and the Hecke algebra are exactly the same computation in from two different points of view for me, because this is the original Janssen picture. Okay, I'll stop there. Thank you.